In this video, I'll show you some examples of catalyzed aldol additions between aldehydes. These reactions are only rarely used for the stepwise preparation of complex organic molecules, but play an important role in many industrial processes for the preparation of various polyols and esters of relatively low molecular weight as solvents and additives for various applications. The beauty of these reactions is that no waste is formed as byproduct, and that even if product mixtures result, these can often be separated by careful distillation. Aldehydes are strongly CH acidic and readily oligomerize, what complicates their storage. Small amounts of bases usually catalyze the aldol addition of aliphatic aldehydes, but unfortunately the product will be similarly reactive as the starting aldehyde and will continue to oligomerize if the reaction is allowed to proceed for too long. In the case of the dimer of acetaldehyde, the so-called acetaldol, a dimerization by acetal formation has also been observed, to yield solid paraldol. If aldehydes are treated with small amounts of acid, some may form cyclic acetals. In the case of acetaldehyde, for instance, mainly two products are formed, the cyclic trimer paraldehyde, a liquid, and the cyclic tetramer metaldehyde, a solid with powerful molluscicidal properties. Large amounts of acid can bring about aldol condensations of enolysable aldehydes. Acetaldehyde, for instance, yields croton aldehyde. This condensation reaction sometimes also occurs just during the long-term storage of aldehydes, because autooxidation can convert aldehydes into carboxylic acids, which then catalyze the aldol addition and condensation. Thus, the stabilization of aldehydes seems to be almost impossible, because any kind of additive triggers some kind of oligomerization reaction. Fortunately, it has been found that very small amounts of bases, for instance 0.5 ppm of sodium hydroxide, can significantly enhance the stability of aliphatic aldehydes and allow their storage for several months at room temperature. Then, alpha-branched aldehydes, such as isobutyraldehyde, are more stable than unbranched aliphatic aldehydes. Nevertheless, before using any new batch of an aldehyde, its quality should be checked by NMR to avoid surprises. Main advantages of the catalyzed aldol addition of aldehydes is that the starting materials and catalysts are readily available and inexpensive. The reactions are usually also easy to perform once suitable conditions have been found. The main problems are that the outcome of these reactions can be difficult to predict and to control. A large number of side reactions can occur and yields are sometimes low. Most of the catalyzed aldol additions between two different aldehydes use an excess of formaldehyde as one of the two aldehydes, because formaldehyde can only react as electrophile, what limits the number of possible products. When enolysable unbranched aliphatic aldehydes are mixed with an excess of formaldehyde and a strong base, a twofold alpha-hydroxymethylation occurs, followed by Meerwein-Ponndorf reduction to yield a tris-hydroxymethyl alkane and formate. Because hydrogen is a less expensive reducing agent than formaldehyde, in large-scale industrial processes the Meerwein-Ponndorf reduction is substituted by a catalytic hydrogenation, as shown here. To prevent the Meerwein-Ponndorf reduction and the formation of formic acid, which would also neutralize the catalyst and cause the precipitation of salts, in this example trimethylamine was used as base. The aldol addition was stopped after 83% conversion of the starting aldehyde, and unreacted starting materials and trimethylamine were recovered by distillation and recycled. This strategy led to high yields of the triol and only small amounts of waste. This is an example of enantioselective aldol dimerization of propanal. As catalyst, 10% of proline was used, and the major diastereomer was obtained with an incredible 99% enantiomeric excess. In this example, no twofold hydroxymethylation by formaldehyde of the starting aldehyde occurred. Instead, by using a buffered reaction mixture and 10% of a proline-based catalyst, the starting aldehyde was only hydroxymethylated once, with high enantioselectivity and chemical yield. Thus, it is possible to perform high-yielding single hydroxymethylations of aldehydes with formaldehyde. Unfortunately, a number of unexpected side reactions can occur when mixing aldehydes with bases. These are, for instance, the Tishenko reaction, that is the formation of esters from aldehydes in the presence of various catalysts. Other variants of the base or nucleophile catalyzed disproportionation of aldehydes include the Oppenauer oxidation, Meerwein-Ponndorf reduction, and the Cannizzaro reaction. This example shows that Tishenko reactions and aldol additions can occur simultaneously to yield interesting products from simple starting materials. Other potential side reactions include aldol condensations, the aerobic oxidation of the starting aldehydes or the product, benzoene condensation, the Michael addition to electron-deficient olefins or alkynes, and Mannich reactions if primary or secondary amines are present in the reaction mixture. Mannich reactions are particularly problematic when proline or other chiral amines are used as catalyst, because this side reaction will deactivate the catalyst. Here are some further examples of aldol additions between aldehydes, but many more have been reported. Although this is an old reaction, the absence of waste and expensive reagents or solvents make it highly attractive from an environmental and economic point of view, and better catalysts and procedures are constantly being developed, as illustrated by the examples I showed you. The next presentation is about the Friedel-Crafts alkylation of arenes by aldehydes, which has been recently rediscovered by academia, so don't miss it out.